We're going to start a very short unit on simple harmonic motion or oscillation. And our definition of oscillation or simple harmonic motion is going to be that it repeats over and over. Now, there are motions that repeat that are not specifically simple harmonic motion. It has to have a couple other things be true for it. Okay, one is that a restoring force is opposite to and proportional to the displacement. What is that? Okay, let's think of a spring. So, we're taking a spring from a spring stand. So there in this equilibrium position. If I pull it down here, right, X is this way, the force on it is going to be back up, and it's equal to KX. So it's opposite direction and proportional to the displacement. If that's true, then the position is a cosine or a sine function. Okay, in AP Physics 1, they always assume it's a cosine function, but it could be a sine function. I'll talk about that a little bit. Now, two common examples where we'll see it in class are in springs. So, get the spring here. Okay, if this is an equilibrium position, okay, where it would hang by itself, and I pull it up to this position, all those positions A, that's the highest point. It's going to go through B, the equilibrium position, and then it'll go down past that, C, each of the low. And then it will just, the springs pull it back up, we go back past the equilibrium, back up to A, and then continue oscillating back and forth between A and C. And if I look at the energies of it, in A, it has a maximum potential energy. And the KE there will be 0. The rest of it turns around at that point. At that point E, the KE is a maximum. PE is a minimum. And then at point C, it's back to all being PE. PE is maximum. And the KE is 0. And it's just going to keep going back and forth. We change from potential energy to kinetic, to potential back to kinetic. And if we ignore friction, we continue to do that forever. Now, the other example is a pendulum. For a pendulum, you experience it, put mass on it, elevate it, take your point A, it's going to swing down B, and then it's going to end up this side. It's a point C, and again, it's going to swing back and forth like that. And we're going to find the exact same things. A is its highest point, so the PE is a max. The KE is 0. When it gets to point B, it's lost its potential energy. The potential energy is minimum. And the KE is max. And then at point C, PE is max again. And the KE is 0. So these are very, very similar. As far as the restoring force, X has pulled it up this way, and the net force on it is going to be back down the other way. It's going to be back down. So again, we have the force in the opposite direction as the displacement. Now, the math we're going to do with this, if I was to graph its position as a function of times here, the spring, we're going to assume for the spring floating up to its highest point and dropping it. So it's going to start high. It's going to go down. We're just going to go back and forth like this. And I'm going to label some things. We're going to call this A. This A stands for apple. Right. Now, this here, this time, for it to repeat, we're going to call it period. That is the time to repeat once. Okay, it is the seconds per cycle. Okay. This from here to here, one cycle would be the time for that, so seconds per one cycle. Frequency is how quickly it repeats, so it is the cycles per second. And if I look at that, period is seconds per cycle, frequency is seconds per second, so the period and the frequency are reciprocal to one another. If I put this all together, I can find the position at the mass on the end of the spring, say, at any point in time by using this equation, which is on reference table. Now, this is going to be a little different. We've almost always had to have our calculators in degrees, but this argument for the cosine has to be in radians. Now, the period depends on the physical properties of the system. Okay. For a spring, period of the spring is going to equal 2 pi square root m over k. The greater the mass, the slower it's going to move, and the longer the period is going to be, the greater the spring constant, the stronger the spring is, it's going to bring it back up more quickly. And for a pendulum, the period of the pendulum is going to be 2 pi square root L over G. G is the acceleration of gravity, and L is the length of the pendulum. So, we have some mathematical examples at the top of the next page. So, the first one, I wrote the equations back over here so we can refer to them. We have a mass of 200 grams suspended from the spring, raise the distance at 30 centimeters, and then drop. So let's take a look at what we're given here. We have a mass of 200 grams. We need to convert that, that's 0.2 kilograms. Because the spring constant is 15 per meter. Now, to raise the distance of 30 centimeters from its rest position, that's the farthest away it's going to be, so that's the amplitude. 30 centimeters, we have to remember to convert that to meters, so 0.3 meters. So that's what we've been given. And then in part A, it says what is the period of the system. So part A, we look at the period. Now this is a spring, so we're going to use this right here. So the period of the spring is 2 pi square root m over k. 2 pi times the square root. The mass was 2, and k was 50, and that's going to give me a value of 0.397. Okay, now part B says what is the frequency? Frequency and period are reciprocals. So I can say the frequency is 1 over the period, 1 over 0.397, and that's going to give me a value of 2.516 cycles per second. C, write the equation for the position. So our general formula is x is a cosine 2 pi f times t. We figured out that a for this one is 53. And we just figured out the f, it is 2.516 times t. Part B is find the position 3 seconds after complete, so we're just going to plug in this equation. X is 3 cosine 2 pi times 2.516. And now we're going to plug in times 3. And if we solve that, that'll get that equals negative 286 meters. And then the last part, E. What time will it reach its lowest position? There's a couple ways to do this. I'll do it the long way first, and I'll show you how to short. Okay? If its highest position is at plus 0.3, its lowest position is going to be minus 0.3. So I have to do minus 0.3 minus t. So if I divide by the 0.3, I get negative 1 is cosine of 2 pi times 2.516 times t. Then I would do the inverse of the cosine, and I would end up actually with pi equals 2 pi times 2.516 times t. If I solve this, I end up with a time of 199 seconds. So that's one way to get the answer. The other way is if we physically think of what's happening here. Right? Okay, so like this. Okay, here's the lowest point that I'm trying to find. I have found that the period way back up in part A was 0.397 seconds. Okay? Well, the lowest point is halfway through the period. So here the t is going to be 1/2 of 0.397. And depending on the rounding, I'm going to end up with the same answer here. So that was kind of a shortcut. If you physically know what's happening in your graphing, you can do it without doing all that math. Now, the problem at the top of the next page, this time I've given it a graph. It says it's a 2 kilogram mass oscillating up and down. And it says find the amplitude, period, and frequency. So we'll do that up here. Okay, the amplitude is how far it is from its equilibrium position. The amplitude is meters. The period is the time it takes to repeat. So it takes 3 seconds for the period. And then the frequency is 1 over the period, so it's 1 over 3 cycles per second. Now, part D, write the equation for the position. So part D, our general formula is X is A cosine 2 pi f t. Now that we have values for A and for f, we can plug those in. Okay, so I end up with X is 4 times cosine 2 pi times 1/3 times t. I can rewrite that just to make it a little bit prettier as 2 pi over 3 times t. Then part C says use the equation to find the position at t equals 2 seconds. This is kind of a verification, but if you look on here, the position at 2 seconds is minus 2, so we should get the same value. So X is 4 cosine times 2 pi over 3 times 2. So X is, now if we plug that into the calculator, we are going to end up with minus meters. So it verified what we expected. Part D is find the spring constant, so I'm looking for K. Alright, now, we can go back to this equation. Ts is 2 pi square root down over K. Plug in our values for T and for n. So the period was 3 equals 2 pi square root. Alright, the mass, I go back up here, 2 kilograms, 2K. And if we solve that, we end up with a value of K. It is 0.877 meters per meter. Okay. Now part E, what is the potential energy stored in the spring? E. So now we have to go back to our energy unit. And we know the potential energy stored in a spring is 1/2 kx squared. So it's 1/2. K is 0.877. And x equals 4. Square that. I end up with potential energy stored in the spring of 7.016 joules. It says, what is kinetic energy at equilibrium? That spring energy is going to turn into kinetic energy. So by the time we get back to equilibrium, the kinetic energy is going to be 7.016 joules. Because the PE has turned into KE.